Something is wrong with the way we picture galaxies. When most people imagine one, they see a graceful spiral turning through the darkness, arms glowing with newborn stars. But the universe never agreed to that single design. Some galaxies are enormous, featureless swarms that stopped making stars billions of years ago. Others are so faint they can hide in plain sight, containing the mass of a giant while looking almost completely empty. Some are being ripped apart, twisted into perfect rings, or lit up from within by a monster black hole, tearing matter to shreds. And here is the strangest part of all. The same galaxy can belong to 4 completely different categories at once, depending on how you look at it. Tonight, you will finally understand why. Before we get into it, if you find these kinds of deep dives into space fascinating, a quick like or subscribe would really help the channel keep growing. It only takes a second, but it means a lot to me. Now, let's begin. Look up at a truly dark sky, and you will see a band of soft light stretching from one horizon to the other. That is our galaxy seen edge on. For thousands of years, human beings looked at that band and had no idea what they were seeing. Some cultures said it was a river of milk. Others said it was a path made by souls. Nobody knew that it was a rotating disk of hundreds of billions of suns, and that this disk was just one example of a kind of object that fills the universe by the trillions. Before we can talk about the many different kinds of galaxies that exist, we first have to be honest about what a galaxy actually is. Because most people carry around a definition that is not quite right. A galaxy is not just a large group of stars. That definition sounds reasonable, but it fails almost immediately. A globular cluster contains hundreds of thousands of stars, sometimes over 1 million, packed into a tight sphere. It is a large group of stars, but it is not a galaxy. A rich open cluster in the disk of the Milky Way can contain thousands of young stars, all born together from the same cloud. It is a group of stars. It is not a galaxy either. The difference is not just size, it is structure, composition, and above all, the invisible framework of dark matter that holds a real galaxy together. A galaxy, properly defined, is a gravitationally bound system containing stars, the remnants of dead stars, gas, dust, dark matter, and in most cases, a central supermassive black hole. Every one of those ingredients matters because the proportions vary enormously from one galaxy to the next. Some galaxies are almost pure old stars with no gas at all. Others are more gas than stars, still building themselves out of raw hydrogen. Some are dominated so completely by dark matter that the visible stars are like faint decorations on top of a much larger invisible mass. That mix, that recipe, is what makes each galaxy different. It is also what makes classification so much more complicated than it first appears. Let us clear up a common confusion right away. A galaxy is not the same thing as a nebula. A nebula is a cloud of gas and dust, sometimes glowing from the light of nearby stars, sometimes dark and cold. Nebulae exist inside galaxies. They are ingredients, not the whole meal. A galaxy is not a galaxy group or a galaxy cluster either. Those are collections of galaxies bound together by their mutual gravity, sitting inside an even larger halo of dark matter. Individual galaxies are the members of those clusters, and a galaxy is not a solar system. A solar system is one star with its planets. A galaxy contains hundreds of billions of solar systems, orbiting a shared center. Where does a galaxy actually end? This is one of the strangest facts about them. Galaxies do not have sharp edges. When you see a beautiful photograph of a spiral galaxy, the arms and disk fade smoothly into the black background of space. There is no crisp boundary, and even that visible starlight is only part of the story. Around every large galaxy stretches an enormous halo of dark matter, an invisible cloud that can extend 10 times farther than the stars we can see. If you define the Milky Way by its visible starlight, you might say it is about 100,000 light years across. If you defined it by the reach of its gravitational pull through its dark matter halo, it might be closer to 1 million light years across. Same galaxy, 10 times the size, depending on where you draw the line. That difference between visible starlight and total gravitational reach is one of the most important ideas in this whole story. It means that a galaxy's brightness and a galaxy's mass are not the same thing. Some galaxies are enormously massive, but produce very little visible light, because their stars are spread out too thinly, or because dark matter dominates. Others look bright and dense, but do not actually contain very much mass compared to what you would guess from the glow. If you only trust your eyes, you will misjudge galaxies constantly. Astronomers have learned to trust gravity instead, tracing motions of stars and gas to figure out what is really there. Galaxies also come in an enormous range of sizes. At the tiny end, an ultra-faint dwarf galaxy might contain only a few thousand stars, barely a step above a star cluster in terms of stellar count. At the giant end, a supergiant elliptical galaxy sitting at the center of a rich cluster can contain trillions of stars, more than 1,000 times as many as the Milky Way. That is a range of about 1 billion in stellar population between the smallest and the largest galaxies. No other kind of astronomical object spans such a range while still counting as the same category. Now, here is where things get complicated in a way that most people never hear about. Galaxy classification is not like classifying animals into species. You cannot just look at a galaxy, note its shape, and file it under one label forever. A galaxy can belong to several categories at once, because different categories describe different things. Consider a real example. Imagine a galaxy that has a beautiful spiral shape with a bar of stars cutting through its center. By shape, it is a barred spiral. Now imagine that same galaxy is currently forming stars at 10 times the normal rate, because a smaller galaxy passed near it recently. By its star formation activity, it is also a starburst galaxy. And now imagine that the same galaxy has a black hole at its core that is actively feeding, blasting out radiation across the electromagnetic spectrum. By its nuclear activity, it is also a Seyfert galaxy, and if the visible stars in its outer disk are spread thinly across a large area, it might also qualify as a low surface brightness galaxy. One galaxy, 4 labels, all correct at the same time, because each label is answering a different question. Shape is one question, size is another, brightness distribution is another, star formation rate is another, central black hole behavior is another, the environment the galaxy lives in is another. Each of these can give you a different classification. When astronomers talk about the 18 main types of galaxies we will explore, they are not carving the universe into 18 exclusive boxes. They are giving us 18 useful ways to describe what a galaxy is doing and where it comes from. Some galaxies fit cleanly into just one type. Many fit into several. And most importantly, a single galaxy can change categories over billions of years as it evolves. Astronomers observe galaxies across many different kinds of light. Visible light, the kind our eyes can see, shows us stars and the glowing gas near them. Ultraviolet light picks out young hot stars and regions of active star formation. Infrared light passes through dust and reveals what is hidden behind it, along with older, cooler stars and warm dust itself. Radio waves can trace clouds of cold hydrogen far beyond the visible edge of the disk, as well as the powerful jets from feeding black holes. X-rays reveal million-degree gas and the accretion disks around black holes. Spectroscopy, splitting light into its component wavelengths, tells us what elements are present, how fast things are moving, and what conditions the gas is in. A galaxy that looks like one thing in visible light can look like something completely different in infrared or radio. Both views are real. Neither one alone tells the whole story. There is one more twist before we get into the specific types. A galaxy's appearance depends on how you are looking at it. A spiral galaxy seen face-on shows its arms and central bulge beautifully. That same galaxy seen edge-on looks like a thin line with a bulge in the middle. The physical galaxy has not changed. Your viewing angle has. Astronomers have to be careful about this. When they see an elongated shape, they have to figure out whether the galaxy is actually elongated in 3 dimensions, or whether it is a rounder shape being viewed at an angle. This is why classifications based purely on apparent shape can sometimes mislead. The universe does not politely present each galaxy at the ideal angle for identification. And there is one more factor that shapes what we see: distance. When we look at a very distant galaxy, we are not seeing it as it is now. We are seeing it as it was billions of years ago, because its light has taken that long to reach us. This means that when we look far away, we are also looking back in time. The galaxies we see in the very distant universe do not look like the galaxies near us. They are smaller, more turbulent, more clumpy, and often more irregular. They are still under construction, trying to force these young, high redshift galaxies into the neat classification categories designed for nearby mature galaxies does not really work. It is like trying to classify a child using the categories designed for adults. The categories do not quite fit, because the objects are at a different stage of their lives. With all of that groundwork laid, we can finally begin our tour through the great families of galaxies. And the natural place to start is with the most famous shape of all, the one that comes to mind when most people picture a galaxy: the spiral. A spiral galaxy is a flattened rotating disk of stars, gas, and dust, with a central bulge of older stars, spiral arms sweeping outward through the disk, and an invisible halo of dark matter surrounding everything. That description alone hides a lot of physics. Why is the disk flat? Why does it rotate? Why do the arms exist? Each of these questions has a real answer. The flatness comes from angular momentum. In the early universe, gas began to fall together under gravity, drawn into a halo of dark matter that had already formed. That gas was not perfectly still. It carried a small overall rotation. As gravity pulled it inward, it could collapse freely along the axis of that rotation, but not perpendicular to it. Anything moving perpendicular to the rotation axis felt a centrifugal effect that kept it spinning around, unable to fall all the way in. So the gas settled into a disk. It is the same principle that flattens a spinning ball of pizza dough when you toss it. Once the disk forms, stars begin to condense out of the gas, inheriting the same rotation. That is why spiral galaxies rotate as coherent structures. It is also why they are flat rather than spherical. The central bulge is different. The stars there formed earlier, before the disk had fully organized itself, or they were driven inward by mergers and instabilities over time. They tend to be older, redder, and to move on more three-dimensional orbits rather than staying neatly in the plane of the disk. Around the whole system stretches the halo, containing globular clusters of ancient stars, individual halo stars, and mostly dark matter. The halo does not rotate the way the disk does. It is a more chaotic structure, a leftover fingerprint of the galaxy's assembly. Then there are the arms, which are what gives spirals their name. And here is where a common misunderstanding needs to be cleared up. The spiral arms are not solid streams of stars being dragged behind the galaxy like ribbons behind a spinning fan. Stars do not stay locked inside one arm as the galaxy turns. If they did, the arms would wind up tighter and tighter with each rotation until they disappeared. That does not happen. So what are the arms really? The best current understanding involves density waves. Imagine a wave of slightly higher gravitational pull moving around the disk. As gas clouds drift into this wave, they get compressed. Compressed gas is exactly what star formation needs. It collapses into new stars, and among those new stars are massive, hot, blue stars that shine incredibly brightly. Those bright young stars are what light up the arm. They burn out fast, in a few million years, but there are always new ones being born as more gas passes through the wave. So the arm is not a stationary river of stars. It is a slow-moving traffic jam, illuminated by whatever gas happens to be inside it at the moment. The individual stars move through the arm. The arm itself moves at a different speed. That is the classical density wave picture. But real spiral arms are messier than any single theory. Some spirals appear to be produced by local instabilities in the disk that come and go over time, creating transient arm-like features rather than a permanent pattern. Some galaxies have two beautiful, clean, long arms wrapping around them. These are called grand design spirals, and the galaxy known as M81 is a famous example. Other galaxies have arms that look broken up into patches and fragments without a clear overall structure. These are called flocculent spirals, and their arms are probably produced by local star formation, triggering more star formation nearby, rather than by any single galaxy-wide wave. Both kinds exist. Neither is wrong. The universe does not require every spiral to be built by the same mechanism. Astronomers who study spirals often sort them into subtypes based on two features: how tightly wound the arms are and how prominent the central bulge is. These are labeled SA, SB, and SC. An SA spiral has tightly wound arms and a large central bulge. An SC spiral has loosely wound arms and a small central bulge. SB sits in between. It is important not to read this sequence as a timeline of evolution. A spiral does not necessarily start as one type and slowly transform into another as it ages. These are just descriptions of what different spirals look like right now, and different spirals may have arrived at their current form through very different histories. Our own Milky Way is a spiral, though we cannot see the whole thing from the inside. Andromeda, our nearest large neighbor, is also a spiral, and photographs of Andromeda are the closest thing we have to a portrait of what our own galaxy probably looks like from the outside. Andromeda is a somewhat more massive spiral than the Milky Way, with a larger disk and a more prominent bulge. Both are broadly similar to what an SB classification would describe. Now, right alongside spirals in the classification schemes sits their close relative, the barred spiral. A barred spiral galaxy is one that has an elongated concentration of stars extending straight through its central region, before the spiral arms begin. This bar is not a solid object. It is a coherent pattern of stellar orbits, the result of instabilities that naturally develop in rotating stellar disks over time. When a disk of stars settles into rotation, small perturbations can grow, and one of the most common results is an elongated bar structure that rotates as a unit while individual stars follow organized paths through it. Bars do real work in a galaxy. They redistribute angular momentum between the inner and outer disk. They can funnel gas from the outer regions of the disk inward toward the center, where that gas can fuel new star formation, feed a growing central bulge, or even reach the very center and feed a supermassive black hole. In some barred spirals, this inflow of gas creates a bright ring of new stars around the central region, a feature astronomers call a nuclear ring. Bars strengthen and weaken over cosmic time. A galaxy that has a weak bar today might develop a stronger one over the next billion years, or lose the bar entirely if enough gas is stripped away. Barred spirals get their own subclassifications, SBA, SBB, and SBC, following the same logic as the ordinary spirals. And just like ordinary spirals, these are descriptions of current appearance, not stages in a required evolutionary sequence. Here is a fact that surprises many people. The Milky Way is a barred spiral. For a long time, our own galaxy was described simply as a spiral. But as observations improved, particularly infrared surveys that could see through the dust in the disk to map the distribution of stars in the inner galaxy, astronomers realized that there is a distinct bar structure in the central region of the Milky Way. Our galaxy carries a bar of stars roughly 10,000 light years long across its middle. So when you look up at the band of the Milky Way, you are looking at a barred spiral from the inside. Barred spirals are not rare or malformed versions of ordinary spirals. Something like half or more of all disk galaxies in the local universe show a bar of some kind. Bars are a normal outcome of disk dynamics, not an oddity. Whether a given disk develops a strong bar, a weak bar, or no visible bar at all depends on details of the disk's mass distribution, its dark matter halo, its gas content, and its history of interactions with other galaxies. Alongside spirals and barred spirals sits a third disk-shaped family, one that is often overlooked, but is very important for understanding how galaxies evolve. The lenticular galaxy. A lenticular galaxy has a disk and a central bulge, just like a spiral, but it does not have prominent spiral arms. Photographs of lenticulars often show a smooth, featureless disk with a bright bulge in the middle, sometimes with a faint hint of structure, but nothing like the dramatic arms of a spiral. For a long time, lenticulars were described as the missing link between spirals and ellipticals, a kind of intermediate form. This description captures something real about how they look, since they share the disk of spirals and the smoothness of ellipticals. But it is important not to take this too far. Lenticulars are not necessarily each individual spiral in the process of turning into an elliptical. They can form in several different ways, and treating them as a mandatory transitional phase would oversimplify a much richer picture. Many lenticular galaxies contain relatively little cold gas, especially compared to spirals of similar mass. Because cold gas is the raw material for new stars, lenticulars tend to have low current star formation rates. Their disks are populated mostly by older stars, giving the whole galaxy a redder, calmer appearance than the blue, active look of many spirals. So how do lenticulars end up this way? Several pathways are possible. One is environmental. When a spiral galaxy falls into a dense galaxy cluster, it plows through the hot gas that fills the space between cluster galaxies. This oncoming pressure can sweep the spiral's cold gas out of its disk, a process called ram pressure stripping. Imagine holding a wet sponge out the window of a fast-moving car. The rushing air blasts the water out of the sponge. In the same way, the hot cluster gas blasts cold gas out of an infalling spiral. The stars stay because they are held tightly by gravity and are far too small to feel the pressure meaningfully. But the gas leaves. Once the gas is gone, star formation stops. The bright blue star-forming spiral arms fade over hundreds of millions of years, until only the smooth disk of older stars remains. What is left looks like a lenticular. Another pathway is exhaustion. A galaxy that is not in a cluster can still gradually use up its supply of cold gas through ongoing star formation, without enough new gas falling in to replace it. Over billions of years, the star formation rate declines, the arms fade, and again a lenticular-like structure emerges. Minor mergers with smaller galaxies can also disturb a disk, redistribute gas, and puff up the bulge, contributing to a lenticular appearance. So lenticulars are best understood not as one thing with one origin, but as a category of end-state disks. They are galaxies that still have their overall disk structure, but have lost the ability to maintain bright arms. We have covered 3 of the disk-shaped families so far. Now we turn to a shape that is completely different. The elliptical galaxy is not a disk at all. It's a 3-dimensional ellipsoid of stars, ranging from nearly spherical to noticeably elongated. Astronomers label ellipticals from E0 for the roundest to E7 for the most elongated. As with all shape-based classifications, this rating describes how the galaxy appears to us, and viewing angle can affect it. A slightly elongated elliptical seen along its long axis will look rounder than it truly is, and the same galaxy seen from the side will look more elongated. So E numbers are honest descriptions of appearance, not perfect measurements of true shape. Ellipticals do not have a thin, cold, rotating disk of stars the way spirals do. Instead, their stars move on a wide variety of 3-dimensional orbits, plunging through the galaxy in many directions rather than circling neatly in one plane. This does not mean ellipticals have no rotation at all. Many of them do rotate to some extent, and some rotate quite significantly. But the disordered orbital motion is generally more important than any coherent spinning. Most ellipticals are dominated by old stars, contain relatively little cold gas, and form very few new stars. They often glow with a warmer, redder light than spirals. They tend to be surrounded by extended halos of hot X-ray emitting gas, particularly the more massive ellipticals, and to host large central, supermassive black holes. In the giant ellipticals found at the centers of rich clusters, these central black holes can reach masses of billions of times that of our Sun. How do ellipticals form? A major pathway is through mergers. When 2 spiral galaxies of comparable size collide and merge over hundreds of millions of years, their neat rotating disks are largely destroyed. The ordered rotational motion of each disk is converted into disordered stellar orbits. Gas is driven into the center, where much of it is quickly consumed in a burst of star formation, or ejected in powerful outflows. What remains after the merger settles down looks a lot like an elliptical. Repeated mergers over cosmic time can build the very largest ellipticals, especially in dense environments where merger rates are high. But it is important not to overgeneralize. Not every elliptical formed through the same sequence of events. Some smaller, compact ellipticals may have formed early in the universe and simply stayed compact. Some may have grown mainly by accreting many small satellites rather than through single major mergers. Ellipticals are a family of endpoints reached by different roads, not a single species with a one origin. And then there is the last of the classical 5 families we need to cover before moving on, the irregular galaxy. Irregulars are galaxies that do not fit neatly into the spiral, barred spiral, lenticular, or elliptical categories. Their morphology is disordered, asymmetric, or otherwise not organized around a clear central axis. But irregular does not mean random or structureless. It just means the structure they do have does not fit the templates designed for other galaxies. Irregular morphology can arise for several reasons. A galaxy may be too low in mass for its gravity to organize a stable disk. A galaxy may be currently being disturbed by a nearby larger galaxy pulling on it tidally. It may be in the middle of an intense burst of star formation that is churning up its gas. Its disk may have been disrupted by a recent merger, or it may have too much turbulent gas and not enough time to settle down. The Large Magellanic Cloud and the Small Magellanic Cloud, our own galaxy's nearest neighbours, are the classic examples. Both are irregular in overall shape, both are strongly influenced by the gravity of the Milky Way, and both contain plenty of gas and ongoing star formation, despite their disordered appearance. Some irregulars retain a partial bar or an asymmetric disk, suggesting they might be underdeveloped or heavily perturbed spirals. Others are more thoroughly disrupted. Irregular galaxies are much more common in the early universe than they are today. When astronomers look at galaxies at very high redshift, seeing them as they were when the universe was young, a large fraction of them look clumpy, chaotic, and irregular. Part of this reflects a real difference. Early galaxies were still assembling, more gas-rich, more turbulent, more prone to interactions. But part of it also reflects observational limits. Distant galaxies are small in our images, and features that would be clearly visible up close blur together into an irregular-looking blob at great distances. So the early universe was more chaotic, but not quite as chaotic as the images alone suggest. We have walked through the 5 great classical families now, the shapes that dominate almost every diagram of galaxies you will ever see in a textbook. Spirals, barred spirals, lenticulars, ellipticals, and irregulars. But if you were to take a proper census of the universe, if you were to actually count how many galaxies of each kind exist, you would discover something surprising. The galaxies we have talked about so far, the bright, photogenic ones that fill the covers of astronomy books, are the minority. The vast majority of galaxies in the universe are small, faint, and often overlooked. If galaxies were a population, the giants and grand spirals would be the celebrities, and the dwarfs would be everyone else. Everyone else, in this case, means most of the universe. To understand galaxies properly, we cannot skip over these smaller systems. They are not just miniature versions of the big ones. Many of them are shaped by different physics, live in different environments, and follow different histories. Some of them are so faint, they were only discovered in the last few decades. Others contain such an extreme ratio of dark matter to visible matter that they behave almost like ghostly gravitational shells with a sprinkling of stars inside. And along the way, we will also visit the opposite extreme. The largest galaxies of all, which grow by devouring their neighbors, and which sit like queens at the centers of galaxy clusters, surrounded by the wreckage of everything they have consumed. Let us start with the dwarf ellipticals. A dwarf elliptical galaxy has the same broad kind of smooth, rounded light distribution as a giant elliptical, but it contains far fewer stars, sometimes only a few 100 million, and it is much less massive. They tend to be found in dense environments, orbiting larger galaxies or living inside galaxy groups and clusters. Two famous examples sit near the Andromeda Galaxy. M110 is a classic dwarf elliptical, while M32 is a related compact system. Both are dwarf ellipticals, and both are close enough to Andromeda that their gravity has been significantly disturbed by their giant neighbor. For a long time, the assumption was that dwarf ellipticals are just scaled-down versions of giant ellipticals, formed by the same processes but smaller. That assumption turns out to be too simple. Many dwarf ellipticals appear to have started life as small disk galaxies or dwarf irregulars, and to have been transformed into their current smooth, gas-poor state by environmental effects, falling into a galaxy cluster, plowing through hot intracluster gas, being tugged by tides from larger neighbors. All of these can strip a small galaxy of its gas, quench its star formation, and eventually reshape it into something that looks like a dwarf elliptical. So the dwarf ellipticals and clusters may not all be born looking that way. Many are made, not born. Very close to dwarf ellipticals sits an even fainter family, the dwarf spheroidals. Dwarf spheroidal galaxies are extremely faint, extremely diffuse systems, containing anywhere from a few thousand to a few tens of millions of stars, spread across regions that can be a few thousand light years across. If you dropped a dwarf spheroidal onto the same patch of sky as a bright globular cluster, the cluster would outshine it dramatically, even though the dwarf spheroidal is a much larger structure by volume. That is how spread out and faint these things are. The Milky Way has many dwarf spheroidal companions: Draco, Sculptor, Fornax, Sextans, Carina, and many others carry the names of the constellations in which they appear on the sky. Each is a small, quiet, mostly ancient collection of stars orbiting our galaxy. Most of them stopped forming stars long ago, which means their stellar populations are dominated by old, red, low-mass stars. What makes dwarf spheroidals scientifically special is that many of them appear to be extraordinarily dominated by dark matter. When astronomers measure the motions of stars inside a dwarf spheroidal, the stars move faster than they should if only the visible matter were providing the gravity. Sometimes the discrepancy is enormous. The best interpretation is that the visible stars are embedded in a much larger, invisible halo of dark matter, and that halo provides most of the gravitational pull. In some dwarf spheroidals, the ratio of dark matter to visible matter can appear to be 100-to-1, or even higher. That makes them the most dark matter-dominated systems we know of. But it is important to say clearly that measuring the dark matter content of a dwarf spheroidal is genuinely difficult. Only a limited number of individual stars can be measured for their velocities. Binary stars, where two stars orbit each other, can add spurious motions that inflate the estimate. If a dwarf spheroidal is being tidally disrupted by the Milky Way, it may not be in equilibrium, which breaks some of the standard assumptions used to weigh it. So while the general picture that many dwarf spheroidals are extremely dark matter heavy is well established, the exact numbers for individual galaxies should be treated with appropriate caution. Not every published dark matter estimate is bulletproof. Why do dwarf spheroidals have so little gas and so few young stars? Their gravity is weak because they are so low in mass. That means anything that pushes gas around inside them can push it out entirely. When a dwarf spheroidal did have gas early in its life, the first generation of supernovae, produced by the shortest-lived, most massive stars, could release enough energy to blow much of the remaining gas out of the shallow gravitational well. Once that happened, no more stars could form. Add in tidal stripping and ram pressure stripping when the dwarf orbits into denser regions near its giant host, and it is easy to see why these galaxies have been drained of the fuel they need for continued star formation. Right next to dwarf spheroidals sits their gas-rich cousin. The dwarf irregular galaxy is small, structurally disordered, and still contains meaningful amounts of gas. Because of the gas, dwarf irregulars can continue forming stars, even though their total mass is tiny compared to major galaxies. The Small Magellanic Cloud is essentially a nearby example of this type, though it sits close to the boundary between dwarf irregular and full irregular. Dwarf irregulars tend to look patchy. Star formation happens in clumps here and there across the galaxy, wherever a gas cloud has become dense enough to collapse. Because these galaxies have such weak gravity, the feedback from each burst of star formation has a huge effect. A cluster of newborn massive stars produces strong stellar winds, and, after a few million years, a series of supernova explosions. Inside a large spiral galaxy, this energy would just puff up a local region of the disk without changing much overall. Inside a dwarf irregular, the same amount of energy can drive gas across large fractions of the galaxy, or even eject some of it entirely. Stellar feedback in a shallow gravitational well is a much bigger deal than in a deep one. There is a plausible evolutionary connection between dwarf irregulars and dwarf spheroidals. A dwarf irregular that falls into orbit around a larger galaxy can be stripped of its gas by ram pressure and tidal forces, and can gradually settle into a smoother, gas-poor system that looks a lot like a dwarf spheroidal. This does not mean every dwarf irregular is destined to become a dwarf spheroidal. Isolated dwarf irregulars that avoid dense environments can keep their gas for a long time and continue forming stars indefinitely. But the transformation happens often enough that it appears to be one of the standard ways nature builds dwarf spheroidals. Now we get to a related but distinct type. The blue compact dwarf galaxy is a small galaxy currently undergoing an intense, concentrated burst of star formation. The word blue refers to the color of the light. When many young, massive stars form at once, they produce large amounts of blue and ultraviolet light. That intense high-frequency glow ionizes the surrounding gas, which then emits its own strong emission lines, adding to the blue-tinted appearance. The word compact refers to how concentrated the visible light is, clustered in a small region rather than spread across a large disk. Blue compact dwarfs are important because they show us that a galaxy's visible face can be dominated by a young population that is only a small fraction of its total stellar mass. Underneath the bright bluish burst of new stars, there is almost always an older, redder, more spread out population that has been there for billions of years. If you were somehow able to remove the burst, you would find an ordinary faint, older dwarf underneath. So it would be wrong to call a blue compact dwarf a newly formed galaxy. What is new is the current star formation event, not the galaxy itself. What triggers the burst? Possibilities include a close encounter with another galaxy, gas falling in from outside, or an internal instability that piles up gas in one region until it collapses all at once. Whatever the trigger, the burst cannot last forever. The intense star formation consumes gas quickly, and the resulting massive stars produce winds and supernovae that can drive remaining gas out of the galaxy. After a few tens or hundreds of millions of years, the burst fades, and the galaxy quiets down. If enough gas remains, another burst may occur later. If not, the galaxy transitions toward being a quieter, redder dwarf. Now, let us move to a completely different kind of small galaxy that has caused a lot of excitement in the last decade or so: the ultra-diffuse galaxy. Ultra-diffuse galaxies are systems whose visible size is comparable to that of much larger galaxies, sometimes even comparable to the Milky Way, but which contain so few stars, spread so thinly across that huge area, that they are extremely faint. Some ultra-diffuse galaxies stretch across tens of thousands of light years, yet contain a total number of stars comparable to what you might expect in a much smaller galaxy. The stars are just spread out enormously. Because they are so faint, ultra-diffuse galaxies were mostly missed by earlier surveys. Old photographic plates could not easily pick them up against the sky background. It was only with sensitive digital cameras and dedicated searches that astronomers began to realize how many of these galaxies exist. Dragonfly 44, discovered by a specialized telescope array designed to detect very low surface brightness features, became one of the poster children for the category. What makes ultra-diffuse galaxies scientifically interesting is that their dark matter content varies wildly from one to the next. Some appear to be extremely dark matter dominated, requiring a large invisible halo to explain the motions of their stars and globular clusters. In these cases, the ultra-diffuse galaxy looks like a small galaxy that ended up living inside a much larger halo, perhaps a failed massive galaxy that never converted most of its gas into stars. Other ultra-diffuse galaxies, however, appear to contain surprisingly little dark matter for their size. A few have even been reported to be almost dark matter free, though these claims should be treated cautiously because measuring the dark matter content of such faint systems is genuinely difficult, and the inferred numbers depend sensitively on distance estimates and other assumptions. Several formation pathways are possible. An ultra-diffuse galaxy could form in an unusually large dark matter halo, but never manage to build many stars, either because feedback drove out the gas, or because star formation was inefficient. It could form normally and then be puffed up by strong stellar feedback in an early burst of star formation. It could be an old galaxy that was tidally heated by interactions with a larger neighbor, spreading its stars over a larger area. Or it could have been born with unusually high angular momentum, which naturally produces a more spread out disk. Almost certainly, the class of ultra-diffuse galaxies includes objects that formed in several different ways. There is not one single origin story here. Now, let us shift back to giants. The giant CD galaxy is one of the largest and most dramatic kinds of galaxy in the universe. CD galaxies are enormous elliptical-like systems that sit near the centers of rich galaxy clusters. Their central regions look like ordinary giant ellipticals, dominated by old stars and hosting supermassive black holes. But surrounding the main body is an extended diffuse envelope of stars that stretches out much further than the visible edge of a normal elliptical. In some cases, this envelope fades so smoothly into the intracluster light, the sparse glow of stars floating between cluster galaxies, that no clear boundary exists at all. That extended envelope tells a story. It is made largely of stars that were once part of other galaxies. In the crowded environment of a rich galaxy cluster, smaller galaxies orbit the central region and pass close to the giant at the center. Every time they do, the giant's tidal gravity can strip some of their outer stars. Over billions of years, a CD galaxy accumulates a vast halo of stripped stars donated by every smaller galaxy that has ever come close. It is a genuine cosmic cannibal, though it works by nibbling rather than swallowing whole. The location of a CD galaxy near the gravitational center of its cluster is not an accident. A process called dynamical friction acts on any large galaxy moving through a cluster. As the galaxy sweeps through the surrounding sea of smaller galaxies and dark matter, its gravity pulls those smaller masses slightly toward it, creating a subtle overdensity behind it. That overdensity pulls back gravitationally on the large galaxy, slowly draining its orbital energy. Over a huge span of time, this drag causes massive galaxies to spiral inward toward the cluster center. Once a very massive galaxy has settled at the bottom of the cluster's gravitational well, it stays there, and it becomes an efficient collector of everything else that sinks in later. The result, after many billions of years, is a giant elliptical-like system with a diffuse envelope, a CD galaxy. CD galaxies typically host extraordinarily massive central black holes. Some of the most massive black holes ever measured, with masses of billions of times that of our Sun, sit at the hearts of CD galaxies. The famous elliptical galaxy M87, at the center of the Virgo cluster, hosts a black hole with a mass of about 6,500,000,000 solar masses. This is the black hole that was famously imaged by the Event Horizon Telescope, showing the shadow of its event horizon against the glow of hot infalling material. M87 is often described as a CD galaxy, though not every brightest cluster galaxy is classified in exactly the same way. The precise boundary between an ordinary giant elliptical and a full CD depends on how prominent that extended envelope of stripped stars is, and different astronomers apply the label slightly differently. The largest known galaxies, systems like IC 1101, are CD galaxies. IC 1101 sits at the center of a distant cluster and contains an amount of stellar mass many times greater than the Milky Way's, embedded in an envelope so extended that estimates of its total size vary depending on where you draw the outer boundary. What is not disputed is that it is enormous. It represents an end state that a galaxy can only reach through a very long history of mergers, accretion, and stellar cannibalism in the middle of a rich cluster. From the largest, densest, most star-packed galaxies, we can now swing to the opposite extreme. Galaxies that contain plenty of stars, but are so dim they can hide in plain sight. This is the family of low surface brightness galaxies. To understand the category, we need a simple concept called surface brightness. Surface brightness is essentially how much light you see per unit area on the sky. If you spread a fixed number of stars across a small region, that region will glow brightly. If you spread the same number of stars across a much larger region, each square unit of sky will contain fewer stars, and the whole region will look fainter, even though the total number of stars is the same. Low surface brightness galaxies are galaxies whose stars are spread out enough that any given piece of the galaxy is dim, blending into the background sky. The key point is that low surface brightness does not mean low total mass. A low surface brightness galaxy can contain a substantial population of stars and a large reservoir of gas. It is not necessarily a small or lightweight galaxy at all. It just distributes its material over a large volume. Some low surface brightness galaxies are actually more massive than the Milky Way. They just look faint because their light is diluted across enormous areas. The category is broad. It includes many diffuse dwarf galaxies. It includes extended disk galaxies with unusually low densities. And it includes a rare class of giant low surface brightness galaxies, huge disks that stretch across hundreds of thousands of light years but glow only faintly because their stars are so widely spaced. Malin 1, discovered in the mid-1980s, is a famous example. It has a disk larger than most spirals, yet its stars are so thinly distributed that the galaxy was almost missed entirely by earlier searches. Why do some galaxies form with such low surface densities? Several factors probably contribute. If the gas in a galaxy is spread thinly, it takes longer for any given region to reach the density needed to collapse into stars. Star formation is inefficient at low gas densities. Extended disks, especially those in isolated environments where they are not being compressed by encounters with neighbors, can maintain a stable, low-density configuration for a long time. Low metallicity, meaning a low abundance of elements heavier than helium, can also slow the formation of the dense molecular clouds that are the immediate birthplaces of stars. Add these factors together, and you get galaxies that have plenty of raw material but convert it into stars only slowly. Low surface brightness galaxies also happen to be excellent laboratories for studying dark matter. When most of the visible mass is spread out and diffuse, the rotation of the galaxy is dominated even more strongly by the dark matter halo than it is in a typical spiral. Measurements of the way the gas rotates in these galaxies helped strengthen the case that dark matter is a genuine physical component of galaxies, not an accounting artifact. Historically, low surface brightness galaxies were badly undercounted. Early surveys used photographic plates and simple detection criteria that automatically threw away anything too faint compared to the sky. That built a systematic blind spot into our maps of the universe. As detection methods improved, particularly with digital cameras that could carefully account for the sky background and reveal faint extended features, we started finding these galaxies in enormous numbers. The universe was always full of them. We just did not have the tools to see them. There is significant overlap between low surface brightness galaxies and ultra-diffuse galaxies. Every ultra-diffuse galaxy is by definition a low surface brightness galaxy. But not every low surface brightness galaxy is ultra-diffuse. Ultra-diffuse galaxies are defined by a combination of large size and very low brightness, sitting at an extreme corner of the parameter space. Low surface brightness galaxies as a whole include everything from small diffuse dwarfs to enormous faint disks. The categories overlap. They are not identical. Let me pause here and pull back to compare because we have now covered a lot of ground. Think about the range we have visited so far. On one end sit the dwarf spheroidals, fainter than most star clusters when integrated, dominated by dark matter, containing populations of ancient stars in shallow gravitational wells. On the other end sit the CD galaxies, enormous elliptical-like systems that anchor the deepest gravitational wells in the universe, packed with old stars, harboring the most massive black holes we know of, and surrounded by envelopes of stars stolen from smaller neighbors. Between these extremes sit dwarf ellipticals, dwarf irregulars, blue compact dwarfs, ultra-diffuse galaxies, and low surface brightness galaxies, and all of them are held together by the invisible framework of dark matter, in halos that range from the tiny wells around the smallest dwarfs to the vast cluster-scale halos that support the CD giants. Look at the sheer dynamic range. From a dwarf spheroidal containing a few thousand ancient stars to a CD galaxy containing trillions is a difference of roughly 1 billion in stellar count. And yet both objects are galaxies. Both are gravitationally bound systems of stars, gas, and dark matter. Both were built by processes that trace back to the same early universe, the same cosmic web, the same initial fluctuations in the density of matter. The extraordinary range is not a bug in our classification. It is a feature of how gravity, gas, and time actually work. It is also worth mentioning here that this corner of the galaxy zoo contains some categories that overlap with the classical morphological types we saw earlier. A dwarf spheroidal is technically also a small elliptical-like system, just at an extreme low-mass corner of the elliptical parameter space. A dwarf irregular shares its irregular morphology with the classical irregular family, just at a smaller size. A blue compact dwarf is technically a specific kind of small galaxy in a bursting state. It is simultaneously a dwarf, a starburst system, and sometimes a low surface brightness galaxy underneath its bright core. This kind of category overlap is not a problem to be fixed. It is a reflection of the fact that galaxies do not come pre-labeled. Every classification is a projection of a multi-dimensional reality onto one or two useful axes. Before we move on to galaxies shaped by collisions and rings, there are a few more variations worth knowing about, ones that fit naturally alongside what we have covered. So let us touch on them briefly. Compact ellipticals are small, unusually dense elliptical galaxies. They are much smaller than typical ellipticals, but still packed tightly with stars. Many appear to be the tidally stripped remnants of larger galaxies, or objects that formed compact and then never grew. They are not the same as dwarf ellipticals, even though both are labeled with the word dwarf adjacent. Compact ellipticals are dense. Dwarf ellipticals are diffuse. Both are small in total stellar mass, but they represent very different physical states. Tidal dwarf galaxies are another interesting variation. When two large galaxies interact and merge, gas and stars are pulled out into long tidal tails. Inside those tails, local gravity can become strong enough to gather material into distinct clumps that then evolve as small independent galaxies. These are tidal dwarfs. They are not born in their own primordial dark matter halos. They form out of already processed material stripped from larger galaxies. Because of this, they tend to have relatively little dark matter for their stellar mass, which distinguishes them from most other dwarfs. They are a useful reminder that not every galaxy sits inside its own private dark matter halo. Some are recycled from the debris of others. Tidal dwarfs are also short-lived on cosmic timescales. Because they lack the deep dark matter halo that shelters most galaxies, they are vulnerable to being pulled apart by the same tidal forces that created them. Some may survive as recognizable galaxies for 1 billion years or more. Others dissolve back into the general stellar population of their surroundings. This makes tidal dwarfs interesting laboratories for studying what a galaxy looks like when it forms without a primordial dark matter halo. If tidal dwarfs really contain very little dark matter, they provide a natural test case for how ordinary matter behaves on its own. So far, observations broadly support the picture that they are dark matter poor, though, as always, measuring the mass of small faint galaxies is difficult. There are also the so-called dark galaxy candidates. Every so often, astronomers detect a cloud of neutral hydrogen gas that seems to be gravitationally bound and rotating like a small galaxy, but with essentially no visible stars associated with it. If confirmed, such objects would be galaxies that never managed to convert their gas into stars. Whether these candidates are truly dark galaxies, tidal debris, or something else remains debated. They are worth mentioning because they push the definition of a galaxy right up to its edge. If a system is gravitationally bound, contains gas, and sits in a dark matter halo, but has no stars, is it a galaxy? Different astronomers answer differently. The universe does not owe us clean definitions. Everything we have covered so far shows a common theme. Galaxies come in an enormous range of sizes and light distributions, but that range is not one-dimensional. Total mass, stellar mass, size, surface brightness, dark matter content, and gas fraction all vary somewhat independently. A galaxy can be low in stellar mass, but large in size. It can be high in dark matter content, but low in visible brightness. It can be small and dense, or small and diffuse. It can be large and bright, or large and faint. This multi-dimensional variety is precisely why classification requires so many overlapping categories, and why no single labeling scheme can capture everything at once. We have gone from the smallest and faintest objects that still qualify as galaxies to the largest and most massive stellar systems in the universe. We have seen dwarf spheroidals in which dark matter overwhelms the visible starlight by a factor of 100 or more. We have seen ultra-diffuse galaxies that stretch across huge areas while carrying only modest stellar populations. We have seen CD giants that grow by cannibalizing their neighbors, and by drinking in the leftover stars of a whole cluster's worth of galactic wreckage. And we have seen the low surface brightness galaxies that were nearly invisible to the earliest astronomical surveys, hiding whole populations of galaxies in the sky that we could not detect. All of these galaxies were quietly living their lives while astronomers debated what a galaxy even was. They did not care what we called them. They were pulled together by gravity, held by dark matter, lit by whatever stars they had managed to form. Each one is a snapshot of a story that began with a small overdensity in the early universe and unfolded through gas cooling, star formation, feedback, and interaction over billions of years. But galaxies do not just sit still and evolve in isolation. Some of the most dramatic transformations happen when two galaxies encounter each other, when a smaller galaxy plunges through a larger one, or when a merging pair ends up wrapped around each other in configurations that no isolated evolution could ever produce. That is where our journey goes next, into the galaxies that have been reshaped by collisions, twisted into rings, thrown into new planes, and torn apart into structures that hold together only for a cosmic instant, before continuing to evolve. Those galaxies remind us more clearly than any others that a galaxy's shape is not fixed. It is a moment in a story. There is a common image in popular science of galaxies drifting through space like ships passing in the night, occasionally waving to one another across enormous gulfs of emptiness. It is a peaceful picture, and for many galaxies it is roughly accurate, but it is also incomplete, because scattered throughout the universe are galaxies that are anything but peaceful. Galaxies that have been slammed into by smaller neighbors and blown open like ripples on a pond. Galaxies wrapped in rings of stars that orbit in bizarre sideways planes. Galaxies with long streamers of stars trailing behind them, pulled out into space like the tail of a comet, but on a scale of hundreds of thousands of light years. Galaxies whose central regions contain two distinct nuclei, evidence that they used to be two separate systems that have not quite finished becoming one. These galaxies remind us of something profound. A galaxy's shape is not something baked in at birth and preserved forever. It is a snapshot, taken at one particular moment, of a story that is still being written by gravity, gas, and time. To understand the galaxies we are going to visit next, you have to keep this in mind. A ring galaxy is not a species, it is a phase. A merging pair is not a permanent structure, it is a chapter. Even the most extreme and disturbed galaxies we can see are on their way to becoming something else, and given enough time, most of them will end up looking a lot like the galaxies we already talked about earlier. Let us start with rings. A ring galaxy is exactly what it sounds like. A galaxy that displays a prominent ring of stars, gas, and star-forming regions surrounding a less luminous interior or central region. In photographs, they look almost artificial, like someone drew a bright circle around a fainter center. The most famous example is the Cartwheel galaxy. When you look at an image of the Cartwheel, you see a bright, blue, roughly circular ring about 150,000 light-years across, connected by faint spoke-like structures to a smaller central region. The overall appearance really does resemble a cartwheel, which is how it got its name. How does a galaxy end up looking like this? The classical explanation is a direct collision. A smaller galaxy passes through the disk of a larger disk galaxy, more or less along the axis perpendicular to the disk. When it plunges through, it does not physically slam into most of the stars in the larger galaxy, because stars are so tiny compared to the distances between them. But its gravity slams into everything. That sudden pulse of gravitational disturbance sends a wave of compression rippling outward from the point of impact, moving through the disk of the larger galaxy like a ripple moves outward from a stone thrown into water. As that gravitational wave sweeps outward, it plows into gas clouds in the disk. The gas gets compressed. Compressed gas collapses. Collapsing gas forms new stars, and among those stars are the massive, hot, blue stars that briefly light up their surroundings with brilliant ultraviolet radiation. Along the entire circular front of the outgoing wave, star formation gets triggered more or less simultaneously. The result, after a few tens of millions of years, is a ring of bright new stars surrounding a comparatively darker center that has already used up much of its gas or had it swept outward. That ring shines for as long as its massive stars survive. But those stars only live for a few million to a few tens of millions of years. So ring galaxies are, in cosmic terms, temporary. The cartwheel is the poster child for this collisional mechanism, and astronomers have identified the smaller galaxy that appears to be the culprit, sitting nearby in the sky. But it would be wrong to assume every ring galaxy formed exactly this way. There is another mechanism that can produce rings without any collision at all. If a galaxy has a strong bar in its center, that bar drives gas inward through the disk. In some galaxies, the geometry of the bar and the disk creates resonances, particular orbital patterns where gas naturally piles up at certain radii. Where the gas piles up, star formation is triggered, and the result can be a bright ring of stars at a specific distance from the center. These are called resonance rings, and they form quietly, without any external collision, just through the internal dynamics of a barred disk. So visually similar rings can have completely different origins. A collisional ring galaxy and a resonance ring galaxy might look somewhat alike in a photograph, but they were built by very different physical processes. Careful observations of the gas motions, the stellar populations, and any nearby companion galaxies can usually distinguish them. Hoag's object is one of the strangest ring galaxies of all. It shows an almost perfect ring of bright, young, blue stars surrounding an older, yellowish, spheroidal core with almost nothing in between. It looks like two completely different galaxies stacked together, an elliptical in the middle and a ring on the outside. How something so clean and geometrically perfect ended up existing is still not fully understood. It might be the result of a very specific kind of merger. It might involve gas being accreted from outside onto a smaller central galaxy. It is a reminder that even after decades of study, the universe can still hand us objects that resist neat explanations. The key thing to remember about ring galaxies is that the ring is not, in most cases, material that was thrown explosively outward from the center like debris from a bomb. In collisional rings, the ring is the visible edge of a wave of star formation, propagating through the disk, and the disk itself is still there, just less brightly lit. In resonance rings, the ring is a region where gas has been quietly concentrated by orbital dynamics. In both cases, ring galaxies are temporary. Give a collisional ring galaxy a few 100 million years, and the ring will fade as its bright stars die. The disk will relax, and the galaxy will return to looking more like an ordinary disturbed spiral. Now, closely related in name but very different in structure is the polar ring galaxy. Where a normal ring galaxy has a ring roughly in the plane of the main disk, a polar ring galaxy has a ring or disk of stars and gas orbiting in a plane, sharply tilted with respect to the main galaxy, often close to perpendicular to it. Imagine a normal spiral galaxy, and now imagine that a completely separate ring of stars and gas is wrapped around it going up over its poles rather than around its equator. That is a polar ring galaxy. It is a truly bizarre configuration. In a stable, isolated galaxy, everything tends to settle into a single rotating plane over time. So having two separate rotating structures with such different orientations tells us that the polar ring did not form as part of the original galaxy. It came from somewhere else. The most likely explanations involve interactions with another galaxy. The polar material may have been captured from a smaller galaxy that passed by and had its gas and stars stripped out. It may have been accreted from a stream of gas flowing in from an unusual direction, or it may be the leftover remnant of a merger event that redirected the incoming material into a plane perpendicular to the pre-existing disk. Whatever the origin, once the polar ring is in place, it can persist for a surprisingly long time. Orbits perpendicular to the main disk are actually stable in the gravitational fields of many galaxies, especially if the dark matter halo of the host is roughly spherical. This durability is one reason polar ring galaxies are scientifically valuable. Because the polar material is orbiting in a plane different from the main disk, the way it moves gives astronomers information about the three-dimensional shape of the total gravitational field, including the dark matter halo. Studying polar rings is one of the few direct ways to probe the geometry of dark matter around a galaxy, rather than just measuring its total amount. The central galaxy and the polar ring often have quite different stellar populations and different gas contents, which makes sense given their separate origins. The central galaxy typically has older stars and less star-forming gas. The polar ring often contains gas that is actively forming stars, sometimes producing a clearly younger and bluer population strung around the perpendicular orbit. It is important not to confuse a polar ring galaxy with every galaxy whose gas disk is slightly misaligned with its stellar disk. Small misalignments are common and can be produced by ongoing gas accretion. A true polar ring is dramatic, with a large angular offset, a substantial mass in the polar structure, and a distinct rotational plane. Only a small fraction of galaxies qualify. Now we come to the largest and most diverse family of interaction-shaped galaxies, the peculiar galaxies, sometimes described as merging galaxies. The word peculiar in astronomy is a technical term. It refers to any galaxy whose morphology does not fit the standard categories because it has been distorted by interaction, whether that interaction is ongoing right now or happened recently enough that the scars have not yet faded. The catalogue of peculiar galaxies is enormous. In the 1960s, an astronomer named Holton Arp compiled a famous atlas of hundreds of peculiar galaxies, and researchers still refer to ARP numbers today when discussing famous individual objects. Each entry in the atlas shows a galaxy or pair of galaxies doing something strange. Tails of stars stretching for hundreds of thousands of light years, bridges of stars and gas connecting two galaxies, shells wrapped around elliptical galaxies like ghostly rings, disks twisted into obviously warped, non-planar shapes, double nuclei sitting inside single luminous envelopes. All of these are gravitational fingerprints, marks left behind by past or ongoing encounters. Let us walk through what happens when galaxies interact, because the physics is beautiful and it explains almost everything about the peculiar catalogue. Two galaxies approach one another. As their separation shrinks, each one feels the gravitational pull of the other, but not uniformly. The side of each galaxy closer to its neighbour feels a slightly stronger pull than the far side. This difference in pull is called a tidal force. It is the same physics that raises tides on Earth from the moon's gravity, but on a much larger scale. Over the course of the encounter, the tidal force stretches each galaxy along the line connecting them, and compresses it slightly perpendicular to that line. If the encounter is a slow, deep one, with the two galaxies actually falling toward each other, the tides can pull enormous streams of stars and gas out of each galaxy. These streams become tidal tails. A tidal tail can extend for hundreds of thousands of light years, thin and gracefully curved, drawn by gravity into arcing shapes. The antennae galaxies, a famous merging pair, show two long tidal tails sweeping outward in opposite directions from the merging cores, giving them their name. The mice galaxies, formerly catalogued as NGC 4676, show similar long parallel tails, arranged in a way that vaguely suggests two tiny mice chasing each other across the sky. Tidal tails are made almost entirely of stars and gas that used to be in the ordinary disks of the two galaxies. The interaction pulls them outward, but gravity keeps most of that material bound to the merging system. Over hundreds of millions of years, the tails eventually fall back and become part of the merger remnant. Some smaller fraction may escape as isolated debris, but the bulk returns. Between the two galaxies, gas and stars can be pulled into a bridge, a stream connecting them. These bridges show that the two galaxies are actively exchanging material during their encounter. Around elliptical galaxies that experience mergers in the distant past, faint shell-like structures sometimes remain. These shells are the fossilized remnants of stars that were pulled out on long, radial orbits during a merger. And that pile up at particular radii because of how orbital dynamics work. Shells are one of the ways astronomers can tell that an elliptical galaxy that looks smooth today actually went through a violent merger in its past. Now, here is something important. When two galaxies collide, the stars themselves do not usually collide with each other. Stars are so incredibly tiny compared to the distances between them that a direct physical collision of two stars during a galactic merger is extraordinarily rare. Instead, the stars simply pass through, feeling the collective gravity of the encounter, but not physically touching. Even the densest central regions of the merging galaxies remain, in stellar terms, mostly empty space. This is one of the strangest and most counterintuitive facts in galaxy physics. Gas, on the other hand, does interact. Gas clouds are large enough that they do collide when they meet. When two gas-rich galaxies merge, their gas clouds slam into each other, get compressed, and often trigger enormous bursts of star formation. This is why merging galaxies are frequently also starburst galaxies, which we will explore shortly. The merger drives gas into the central region, the gas piles up, and star formation ignites at a rate far above the ordinary background rate of either galaxy on its own. Mergers can transform galaxies dramatically. When two spiral galaxies of comparable mass merge, the ordered rotation of their disks is largely destroyed. The stars end up on a much wider variety of orbital paths. Over time, after the merger settles down over hundreds of millions to a few billion years, what remains often looks like an elliptical galaxy, or something close to it. This is one of the main pathways for building large ellipticals in the local universe. It is not the only pathway, but it is a common one. However, it would be wrong to say that every merger produces an elliptical. The outcome depends on the mass ratio of the two galaxies, on how much gas is involved, on the geometry of the encounter, and on the environment. If a small galaxy falls into a much larger galaxy, the result is a minor merger. The larger galaxy's overall disk structure survives, though it may be thickened, warped, or slightly disturbed. The small galaxy is essentially eaten. This kind of minor merger happens all the time, and it is one of the main ways large galaxies grow over cosmic time. The Milky Way is currently in the process of consuming the Sagittarius dwarf galaxy through exactly this kind of minor merger, and it has consumed many others in its past. If two gas-rich disks merge, and there is still enough gas left after the initial star formation burst, some of that gas can settle back into a rotating disk around the merger remnant. In some cases, the remnant actually rebuilds itself as a new, larger disk galaxy rather than becoming a classic elliptical. This is one reason we should not treat spiral galaxies as pristine survivors that have never merged with anything. Many spirals have merger histories in their past. Their disks are second-generation structures. If two large gas-poor ellipticals merge, the result is simply a larger, more massive elliptical. And if the environment is rich in galaxies, the merger remnant may itself go on to merge with additional galaxies over subsequent billions of years, building progressively toward the giant CD-type systems we visited earlier. The point is that merging is a process, not a category. A merging pair caught in the middle of the event looks very different from what the two galaxies looked like before, and very different from what the remnant will look like after. If you were to make a movie of a merger slowed down to compress hundreds of millions of years into a few minutes, you would see two spirals approaching, brushing past each other, pulling out tidal tails, falling back together, spiraling in, punching through each other repeatedly, and finally settling into a single galaxy. At every stage, the shape would be different. Classifying that system based on a single snapshot depends entirely on which snapshot you catch. Some peculiar galaxies show clear double nuclei. In photographs, you can see two distinct bright cores separated by a small distance, all surrounded by a single luminous envelope. That is a merger caught in its late stages, where the two original galaxies have almost finished combining, but their central regions have not yet fully coalesced. Over the following few 100 million years, dynamical friction will pull the two nuclei together. If both original galaxies had central supermassive black holes, those black holes will eventually merge too, releasing an enormous burst of gravitational waves as they spiral into one another. Gravitational wave observatories have already detected the ripples from massive black hole mergers, though the most extreme events involving the biggest supermassive black holes are targets for future observatories. Warped disks are another common signature of interaction. A galaxy that has been recently disturbed may show a disk that is not flat. Instead, the outer parts of the disk are bent up or down out of the plane of the inner disk. Warps can be caused by tidal forces from a passing neighbor, by the accretion of gas along an unusual direction, or by the gravity of a misaligned dark matter halo. Our own Milky Way's disk has a real, measurable warp in its outer regions. Some peculiar galaxies show shells. These are faint, arc-like features that surround an otherwise ordinary elliptical galaxy, appearing at different radii like the layers of an onion. Shells are the fossil record of a merger in which a smaller galaxy was captured onto a nearly radial orbit and gradually shredded, with its stars piling up at their turnaround points. Each turnaround becomes a visible shell. By carefully mapping shells, astronomers can reconstruct the parameters of a merger that finished a long time ago. Now, one important idea that comes up repeatedly when discussing interactions is jellyfish galaxies. A jellyfish galaxy is a galaxy currently falling through the hot gas of a rich galaxy cluster, moving fast enough that ram pressure is stripping gas out of it in real time. The stripped gas trails behind the galaxy, forming long streamers full of active star formation, giving the galaxy an appearance eerily similar to a jellyfish with its tentacles trailing behind. Jellyfish galaxies are essentially caught in the act of being transformed. Their star-forming disks are being torn open, their gas is being pulled out and left behind them, and in a few 100 million more years, they will have lost so much of their fuel that their star formation will begin to shut down entirely. Give it long enough, and today's jellyfish galaxy becomes tomorrow's gas-poor lenticular or dwarf elliptical, depending on its size and history. Environment matters here. Galaxies that live in isolation are shaped mostly by their own internal dynamics and by any occasional close encounters with a neighbor. Galaxies and groups experience more frequent close passes, with strong tidal effects and occasional mergers. Galaxies and rich clusters face the harshest environment of all. They plow through hot cluster gas that strips their own gas. They are subjected to frequent high-speed encounters with other cluster galaxies. And in the most extreme cases, they experience a process called galaxy harassment, where multiple high-speed flyby encounters over billions of years cumulatively disturb the disk, heat up the stellar orbits, and transform the galaxy into something more spheroidal and less disk-like. None of these environmental effects operates in isolation. A galaxy in a cluster feels ram pressure stripping, tidal stripping from the cluster's overall gravitational field, harassment from other galaxies, and the effect of its own internal evolution all at once. The result is that galaxies in dense environments tend to lose their gas, quench their star formation, and evolve towards smoother, older-looking morphologies. Galaxies in low-density environments tend to hold onto their gas, keep forming stars, and preserve their disk structures. This is why galaxy morphology correlates so strongly with environment. Ellipticals and lenticulars dominate the centers of rich clusters. Spirals dominate the lower density outskirts and the field. Watching all of this play out through simulations has revolutionized our understanding of interactions. Numerical simulations running on powerful computers can model the gravitational dynamics of billions of particles representing stars, gas, and dark matter, and can reproduce the tidal tails, bridges, shells, and other features seen in real peculiar galaxies. By comparing observations of a specific peculiar galaxy to a simulation, astronomers can often reconstruct the parameters of the encounter that produced its current shape. How massive were the two galaxies? What was their relative velocity? How long ago did they first pass close to each other? Simulations turn the frozen snapshot of a photograph into a reconstructed history. Here is a way to hold all of this together in your mind. Every peculiar galaxy is a story in progress. Its shape is telling you something about what has happened to it recently, and something about what it will look like in a few billion years. A ring galaxy is a galaxy that was hit by a smaller neighbor, and whose ring will fade as the stars in it die. A polar ring galaxy is a galaxy that captured material from somewhere else, and whose perpendicular ring may persist for a long time. A merging pair with tidal tails is a galaxy on its way to becoming a single, larger, elliptical-like remnant. A jellyfish galaxy is a galaxy in the process of losing its fuel and drifting toward gas-poor middle age. None of these systems are permanent. The peculiar catalogue is not a list of stable species. It is a catalogue of galaxies caught in the middle of change, showing us processes that most galaxies go through at some point, and that shape the entire population of galaxies we see today. Consider what this means for morphological classification as a whole. When we look at the population of galaxies in the local universe and see that spirals, ellipticals, and lenticulars have such distinct shapes, we might be tempted to think that each galaxy chose its category early on and stayed there. That is not what happens. Every large elliptical you see today may well have been an even earlier pair of spirals that merged. Every lenticular may have been a spiral that lost its gas. Every peculiar galaxy is on its way to becoming something more ordinary, given time. And every ordinary galaxy is one significant encounter away from becoming peculiar for a while. Compare a ring galaxy to a polar ring galaxy. Both have rings in their names. Both look, at first glance, like galaxies with a ring on them. But their structures are completely different. A ring galaxy has a ring in the plane of its main disk. A polar ring galaxy has a ring perpendicular to its main disk. A ring galaxy is usually the result of a direct collision through the disk. A polar ring galaxy is usually the result of an accretion event from an unusual direction. A ring galaxy's ring will fade in a few 100 million years. A polar ring galaxy's ring may persist for billions of years. Same word, different physics. Compare a merging galaxy to an ordinary spiral. From close up, you can see that the merging galaxy has tidal tails, warped structures, or double nuclei that make its interaction history obvious. But from very far away, the same merger seen at low resolution might just look like a slightly disturbed blob. Distance and resolution matter enormously in classification. A galaxy that we can clearly identify as merging in the nearby universe might be indistinguishable from a compact, irregular blob at the high redshift edge of what we can observe. This is a running theme throughout the story of galaxy classification. Every time we improve our ability to observe, we discover new categories, new subtleties, and new populations that were invisible before. Ring galaxies were rare curiosities in the early days of galaxy surveys. Now we know they represent a common transient phase in galaxy interactions. Polar ring galaxies were once thought to be extraordinary oddities. Now we know they trace a real, if less common, formation pathway. Jellyfish galaxies were only recognized as a distinct category in recent decades. Once large surveys of galaxy clusters made it possible to identify galaxies caught in the act of being stripped. There are still many galaxies whose peculiar shapes have not been fully explained. Some show complicated, tangled structures that do not fit any simple encounter scenario. Some show features that cannot be reproduced by standard simulations without invoking unusual conditions. The universe keeps producing objects that stretch our understanding. This is not a failure of the classification system. It is a reminder that classification is a tool for organizing what we know, not a definitive statement about what exists. And now, having walked through galaxies shaped by shape, by size, and by interaction, we reach the final family in our tour. Galaxies that are classified not by what they look like, but by how they behave. Galaxies defined by the intensity of their star formation, or by the fire burning at their centers where a supermassive black hole is drawing in matter and lighting up the entire electromagnetic spectrum. Those galaxies are our final subject, and they will show us the last dimension of the story. Because in the end, a galaxy is not just a shape or a size. It is a system that lives, feeds, burns, quiets down, and sometimes lights up again as its central black hole wakes from sleep. Everything we have talked about so far in our journey through galaxies has been about shape and structure. Spirals with their arms, ellipticals with their smooth ellipsoidal forms, ring galaxies and polar rings, merger remnants and tidal tails. All of these categories describe what a galaxy looks like or how it is put together in space. But there is another whole dimension to galaxy classification that has nothing to do with shape at all. It has to do with what a galaxy is doing. Is it quietly aging, converting old gas into new stars at a slow trickle? Or is it burning through its fuel at a furious rate, producing new stars 100 times faster than a normal galaxy? Is the black hole at its center dormant, sleeping in the dark? Or is it actively feeding, releasing energy so intense that it outshines the entire host galaxy from a region smaller than our solar system? These questions define the final family in our tour. And what makes these categories so interesting is that they cut across every morphological type we have seen. A starburst galaxy might be a spiral, an irregular, or a merger remnant. A Seyfert galaxy might be a barred spiral or an ordinary spiral. A radio galaxy is usually hosted by a giant elliptical, but not always. These are not shapes, they are behaviors. And the same galaxy can shift between behaviors over cosmic time as its gas supply, its black hole feeding, and its interactions with neighbors change. Let us start with the family defined by extreme star formation, the starburst galaxy. A normal galaxy like the Milky Way forms new stars at a fairly modest rate. Our galaxy produces something like 1 to a few new stars per year, on average, spread across a huge disk. That is a slow, steady drip of star formation. A starburst galaxy is one that is forming stars at a rate 10 times, 100 times, or in extreme cases even 1,000 times higher than that. Sometimes the entire star formation rate is concentrated in a small central region, only a few hundred light years across. Other times it is spread across the whole galaxy. Either way, it is fast, it is intense, and it cannot last forever. To understand why starbursts happen, you have to think about what star formation actually needs. It needs cold, dense gas, gathered in clouds where gravity can overcome pressure and cause collapse. In a quiet, isolated galaxy, gas is spread through the disk in a semi-stable configuration. It forms stars, but not efficiently, because most of the gas is not dense enough at any given moment. What a starburst requires is a mechanism to take large amounts of gas and rapidly funnel it into dense concentrations. Several mechanisms can do this. Galaxy mergers are among the most powerful triggers. When two gas-rich galaxies interact, their gas clouds slam into each other, get compressed, and can lose the angular momentum that was keeping them spread out. Enormous quantities of gas fall inward toward the merging center, pile up in dense concentrations, and ignite in a burst of star formation. This is why interacting galaxies and merger remnants are so frequently classified as starbursts. The starburst is the fingerprint of the interaction, telling us that gas got shaken up recently. Close gravitational encounters, short of a full merger, can also drive gas inward. A galaxy that passes close to a neighbor may feel a tidal disturbance that destabilizes its disk enough to send gas cascading toward the center. Bar-driven inflow is another mechanism. In a barred spiral, the bar's rotation drags gas along orbital paths that bring it toward the central region. If the bar is strong and the gas supply is generous, this inflow can trigger a nuclear starburst in the very center of the galaxy without any external interaction at all. Rapid gas accretion from the intergalactic medium or compression in a dense environment can add further triggers. Whatever the specific cause, the result is the same. Large quantities of gas end up gathered in dense molecular clouds. Stars form fast, and the stars that dominate the light of a starburst are the massive, hot, blue ones, because they are so bright that they outshine the older population entirely. A starburst galaxy in visible light glows blue and blazes with ultraviolet radiation from its youngest stars. But there is a twist. Massive star formation happens inside gas that is often full of dust. The dust absorbs the ultraviolet light from young stars, warms up, and re-radiates that energy in the infrared. This means that many of the most powerful starbursts in the universe are not actually most visible in the ultraviolet or visible bands. They are most visible in the infrared. Some galaxies are so obscured by dust that if you look at them in visible light, you barely see anything interesting. Look at them in the infrared, and they blaze with tremendous brilliance. These are the luminous and ultraluminous infrared galaxies, systems radiating enormous total energies almost entirely at infrared wavelengths because their dust is trapping and re-emitting the ultraviolet from a hidden starburst inside. The nearby galaxy ARP 220 is one of the most famous examples. In visible light, it looks like a somewhat disturbed merger remnant. In the infrared, it is one of the most luminous galaxies in the entire nearby universe. Its central regions are packed with dust and molecular gas, and enormous amounts of star formation are happening inside. But the dust is so thick that most of the visible light never escapes. Starbursts are not permanent. They cannot be, because they eat their own fuel. A galaxy forming stars 100 times faster than a normal galaxy is depleting its cold gas reservoir 100 times faster than normal too. Depending on the total gas supply, A starburst can last anywhere from a few tens of millions of years to a few 100 million years, but not much longer than that. And even before the fuel runs out, the burst tends to shut itself down through feedback. Feedback is one of the most important ideas in galaxy evolution. When massive stars form, they do not just sit there quietly. They pour out intense radiation that can push on surrounding gas. They produce powerful stellar winds that blow material outward. And after a few million years, they explode as supernovae, injecting enormous amounts of energy into their surroundings. Multiply these effects across thousands of massive stars all forming in the same region at the same time, and you get a powerful, coordinated outward push on the surrounding gas. In starburst galaxies, this feedback can drive galactic-scale outflows. Gas that was falling in and forming stars gets pushed back out, sometimes at speeds of hundreds of kilometers per second. In the most extreme cases, these outflows become super winds, blasting hot, enriched material out of the galaxy entirely and injecting it into the surrounding intergalactic medium. The elements that were forged inside stars, carbon, oxygen, iron, and many others, get scattered out of the galaxy through these winds, seeding the wider universe with the raw materials for future stars and planets. The stardust that eventually became you was probably once inside a starburst galaxy that flung it out into space. Super winds regulate starbursts. As gas is expelled and star formation reduces its own fuel supply, the burst tapers off. The galaxy quiets down. It transitions to a lower star formation rate. Depending on how much gas remains and whether it can be replenished, the galaxy may return to normal star formation, or it may enter a genuine quiescent phase where star formation has essentially stopped. Some starburst galaxies are caught by astronomers on their way down in a state called post-starburst. A post-starburst galaxy is one that had an intense burst of star formation not long ago, but has now stopped forming new stars. Its spectrum shows the telltale signature of a population dominated by stars of intermediate age, the ones that were born in the burst and have now aged past their brightest, hottest phase. Related to post-starbursts are a few colourful categories worth mentioning. Green pea galaxies are small, compact galaxies that appear green in survey images because a strong emission line from ionized oxygen falls in the green part of the visible spectrum. They are undergoing intense star formation in very small volumes and are thought to resemble, in some ways, the compact star-forming galaxies of the early universe. Clumpy, high redshift galaxies, seen when the universe was young, look broken up into a few bright star-forming regions rather than showing organized disks or bulges. They are galaxies caught in the middle of assembling themselves. Compact, quiescent galaxies, also seen at high redshift, are the opposite. Small, dense, packed with old stars, and no longer forming new ones, they represent early galaxies that finish their main star-forming phase very quickly. One important complication: not every infrared bright galaxy is powered purely by star formation. Some are powered, at least in part, by an active black hole at the center. Distinguishing between star formation power and active nucleus power requires careful analysis of the spectra, and in many galaxies both contribute at once. That leads us directly into the next great category of behavior-based classifications: the active galactic nucleus. A Seyfert galaxy contains an active galactic nucleus, an extremely luminous, compact region at the center of the galaxy where matter is falling toward a supermassive black hole and releasing enormous energy in the process. Now, right at the outset, we have to correct a very common misunderstanding. The light from an active galactic nucleus does not come from inside the black hole. Nothing can escape from inside a black hole's event horizon, not even light. That is the definition of a black hole. So the enormous luminosity of a Seyfert nucleus is not somehow emitted from the black hole itself. What actually happens is this: a gas that falls toward a supermassive black hole does not usually plunge straight in. It has angular momentum, so it settles into a rotating accretion disk around the black hole. In that disk, the gas spirals inward gradually, and as it does, it loses gravitational potential energy. That energy has to go somewhere. It goes into heat and radiation. The gas in the inner regions of the accretion disk gets extremely hot, millions of degrees, and glows across a huge range of wavelengths, from ultraviolet to X-rays. This radiation is produced outside the event horizon in the accretion disk itself, before the gas crosses the point of no return. Once matter crosses the event horizon, it is gone from view forever, but by then it has already released the energy we see. The result is a compact source of enormous luminosity, sometimes brighter than the entire rest of the host galaxy combined, packed into a region only about the size of our solar system. From far away, this compact nucleus can look like a single blazing point of light. In closer studies, however, we can see the host galaxy around it, and in the case of Seyfert galaxies, the host is often a spiral. That is one of the defining features of Seyfert galaxies. They are usually hosted by ordinary-looking disk galaxies, most commonly spirals. So a Seyfert galaxy is not a fundamentally different shape of galaxy. It is a normal galaxy that happens to have a currently active, supermassive black hole at its center. Seyfert galaxies come in two main flavors, called Seyfert 1 and Seyfert 2. The distinction is based on how they look spectroscopically. A Seyfert 1 shows both broad emission lines and narrow emission lines in its spectrum. A Seyfert 2 shows only narrow emission lines. This may sound technical, but the physical interpretation is striking. The broad lines are produced by gas moving extremely fast, very close to the black hole, where the gravitational pull is enormous. That fast-moving gas Doppler broadens its emission over a wide range of wavelengths. The narrow lines come from gas farther out, moving more slowly, whose emission is not smeared out as much. So if you see broad lines, you are looking at gas very close to the central engine. If you do not see broad lines, either the broadline region does not exist for that galaxy, or something is blocking your view of it. This leads to the unification model of active galactic nuclei. According to this picture, most Seyfert galaxies actually have the same underlying structure. A supermassive black hole, an accretion disk, and around them, a thick torus of dust and gas that obscures the central regions when viewed from certain angles. If you look at a Seyfert galaxy face on to its torus, you see all the way into the broad line region, and you classify the galaxy as a Seyfert 1. If you look at the same galaxy edge on to its torus, the torus blocks your view of the innermost broad line region, and you only see the narrow lines from farther out. You classify the galaxy as a Seyfert 2. In this picture, Seyfert 1 and Seyfert 2 are the same kind of object viewed from different angles. Orientation matters, and the same nucleus can look completely different depending on how you happen to be seeing it. This unification idea has been remarkably successful, and it is supported by observations that reveal hidden broadline regions in some Seyfert 2 galaxies when you use polarized light or infrared observations that can partly see through the obscuring torus. That said, orientation is not the entire story. Some safer galaxies genuinely do not have the same structure as others. Some appear to be intrinsically weaker in broad lines, regardless of orientation. Some may have accretion disks in different states of activity. So the unification model is a useful framework, not a complete explanation. Reality is always a little messier than the simplest model. An important fact to hold on to is that most massive galaxies contain supermassive black holes at their centers. The Milky Way does, Andromeda does, nearly every large galaxy we have carefully examined does, but only a fraction of these black holes are actively feeding at high enough rates to produce a safer nucleus at any given moment. Most of them, most of the time, are quiet. They are surrounded by relatively little gas at their innermost regions, and they release very little detectable radiation. Sagittarius AEI star, the supermassive black hole at the center of our own galaxy, is in exactly this quiet state right now. It has a mass of about 4 million times that of the Sun, but it accretes very little material, and its emission is tiny compared to the vast luminosity of a full Seyfert nucleus. Whether a black hole is active or quiet depends on whether it is being supplied with fresh fuel. A black hole surrounded by gas and disturbed material can feed and light up. A black hole in a settled, gas-poor environment cannot. This means that the same galaxy can switch on and off over cosmic time. A bar-driven flow of gas into the center can wake up a quiet black hole, turning an ordinary spiral into a safer galaxy for a while. A merger can drive massive gas inflow, feeding the black hole intensely. Then, as fuel runs out or feedback pushes the gas back, the accretion slows down and the galaxy returns to a quieter state. So Seyfert activity is a phase, not a permanent identity. Every galaxy with a central black hole is potentially a safer galaxy in waiting, and every current safer galaxy will eventually quiet down when its fuel is gone. Now let us turn to another face of active galactic nuclei, the radio galaxy. A radio galaxy produces exceptionally strong emission at radio wavelengths, associated with an active galactic nucleus and often with enormous jets of matter and energy blasting out from the central region. Here is what happens physically. Around the innermost part of the accretion disk, in the strong gravitational and magnetic environment near a rotating supermassive black hole, some of the infalling matter gets redirected. Instead of falling all the way in and crossing the event horizon, it gets accelerated outward along the black hole's rotation axis, forming a pair of collimated jets. These jets shoot in opposite directions, perpendicular to the plane of the accretion disk. The material in the jets is a hot plasma of charged particles, moving at speeds close to the speed of light. Once again, these jets do not emerge from inside the black hole. They are launched from the region just outside the event horizon, from the innermost parts of the accretion flow, powered by the gravitational and rotational energy of the system. Nothing escapes from inside the event horizon, but an enormous amount of energy can be extracted from just outside it. These relativistic jets travel outward for enormous distances. In the most powerful radio galaxies, they can extend hundreds of thousands or even millions of light years, far beyond the visible galaxy that hosts the nucleus. As the jets travel, they push into surrounding gas, both the gas around the galaxy and the intergalactic gas beyond. Where the jets slam into this gas, they inflate huge lobes of magnetized plasma. Inside these lobes, high-energy electrons spiral around magnetic field lines, emitting a specific kind of radiation called synchrotron radiation. Synchrotron emission is what makes radio galaxies so luminous at radio wavelengths. The classic radio galaxy image shows a small compact host galaxy in the middle, and two enormous radio-emitting lobes extending far to either side. These lobes can be many times larger than the host galaxy itself. Where the jet meets the outer edge of a lobe, we sometimes see a bright hotspot, a place where the jet is decelerating suddenly as it plows into the surrounding medium. Radio galaxies come in two main types, based on the arrangement of their radio emission. In one type, the emission is brightest close to the center and fades outward. In the other, the emission is brightest at the outer edges of the lobes, at the hotspots. These are usually labeled FR1 and FR2, using a classification introduced by astronomers Bernard Fanaroff and Julia Riley in the 1970s. FR1 radio galaxies are typically edge-darkened. They tend to be lower in luminosity, and their jets slow down as they push into denser surroundings. FR2 radio galaxies are edge-brightened. They tend to be much more luminous, with jets that stay collimated over larger distances and produce dramatic hotspots at their ends. Two of the most famous radio galaxies are Cygnus A and Centaurus A. Cygnus A is a spectacular FR2 source. Compact host galaxy, thin jets, and enormous lobes stretching hundreds of thousands of light years on either side. Centaurus A, closer to us, shows a very peculiar host galaxy with a distinctive dust lane, evidence of a past merger, and prominent radio jets extending outward. The M87 galaxy at the center of the Virgo cluster is another famous radio-loud galaxy. Its jet extends thousands of light years from its nucleus and is bright enough to be imaged in visible light, showing knots and structure along its length. Radio galaxies are most commonly hosted by giant elliptical galaxies. This is not an accident. The most massive black holes tend to live in the most massive galaxies, and giant ellipticals sit at the top of the mass ladder. Their black holes, when fed, can drive the most powerful jets. Radio galaxies are also often found in dense environments, particularly at the centers of galaxy clusters, where a rich supply of hot gas surrounds the host galaxy, and where the accretion history has often been active. The relationship between radio galaxies, Seyfert galaxies, quasars and blazars deserves careful attention. All of these are active galactic nuclei, powered by accretion onto supermassive black holes. They differ in luminosity, radio properties, and viewing angle. A quasar is an extremely luminous active nucleus, so bright that in the earliest observations it appeared as an unresolved point of light, indistinguishable from a nearby star, hence the name quasi-stellar. Only later did we realize that quasars are the compact nuclei of very distant galaxies. Host galaxies that are usually too faint to see against the glare of their brilliant central engines. So a quasar is not a fundamentally different kind of galaxy. It is a very luminous active nucleus, sitting inside a host galaxy, viewed from a distance great enough that we mostly see the nucleus. A blazar is an active nucleus whose relativistic jet is pointed almost directly at us. When you look straight down the barrel of a relativistic jet, the jet's emission gets tremendously boosted in intensity and shifted in frequency by relativistic beaming effects. The result is a source that appears extraordinarily bright, rapidly variable, and dominated by non-thermal emission from the jet. A blazar is not a separate species of galaxy either. It is an active nucleus whose jet is oriented favorably from our vantage point. This is where a broader unification picture emerges. The same underlying object, a supermassive black hole with an accretion disk, and possibly a pair of jets, can appear as different classes depending on how you view it and how luminous it happens to be. Face-on view of an accretion disk with modest luminosity, we might call it a Seyfert 1. Edge-on view, obscured by the torus, Seyfert 2. Very high luminosity, dominating the host galaxy, quasar. Jet pointed at us, blazar. Strong radio emission from lobes, radio galaxy. These labels are not describing entirely different objects. They are describing different states, orientations, and luminosity levels of a family of related systems. This does not mean orientation is the only variable. Real active nuclei differ in intrinsic power, in the mass and spin of the central black hole, in the accretion rate, in the fuel supply, and in the properties of the surrounding gas. But orientation is a big part of what makes the same underlying object look so different in different observations. Understanding that has been one of the major achievements of decades of research on active galaxies. Active galactic nuclei also do something remarkable to their host galaxies over cosmic time. The energy released by an active nucleus is not confined to the nucleus itself. It couples to the surrounding gas, both through radiation and through jets. This is called active galactic nucleus feedback, and it is one of the most important effects in galaxy evolution. In some cases, feedback can suppress star formation. A powerful jet can heat the surrounding gas so much that it cannot cool down and condense into new stars. This is thought to be one of the main reasons why the most massive galaxies at the centers of clusters, which should have plenty of gas available to form stars given the amount of hot gas around them, actually form very few stars. Their central black holes have been active enough, often enough, over their lifetimes to keep the surrounding gas too hot for star formation. It is a striking picture. A region of space smaller than our solar system, powered by a black hole, can regulate the star formation across an entire galaxy and even across the surrounding cluster. In other cases, feedback can trigger star formation. A jet pushing into a nearby gas cloud can compress the cloud enough that it collapses and forms new stars. This is a more localized effect, and the balance between suppression and triggering depends on the details of the jet's power, the surrounding density, and the geometry of the encounter. Over long timescales, feedback from active nuclei is thought to be one of the key mechanisms that quenches star formation in massive galaxies, and that connects the growth of central black holes to the growth of their host galaxies. There is a well-known observed correlation between the mass of a central black hole and the mass of the central bulge of its host galaxy. This correlation suggests that black hole growth and galaxy growth are linked, but the exact chain of cause and effect is still being worked out. It is not as simple as saying the black hole controls the galaxy, or the galaxy controls the black hole. They evolve together, and feedback is part of the coupling. Let us bring the entire journey together now. We began with a simple question. What is a galaxy? We saw that a galaxy is a gravitationally bound system of stars, remnants, gas, dust, dark matter, and usually a central black hole. Its boundary is fuzzy, its visible light traces only part of its full extent, and its classification depends on which of many overlapping properties you emphasize. We walked through the classical morphological families, spirals with their rotating disks and density wave arms, barred spirals with their central bars redirecting gas inward, lenticulars with disks that lost the ability to shine as arms, ellipticals with disordered stellar orbits, often built by mergers, irregulars whose disturbed or low-mass structure defies neat categories. We visited the dwarf galaxies, the diffuse systems, and the cluster giants. We saw that most galaxies in the universe are dwarfs. We saw ultra-diffuse galaxies hiding populations of stars across huge volumes. We saw CD galaxies at the hearts of clusters, drinking in the stars of their neighbors over billions of years. We saw low surface brightness galaxies that eluded early surveys entirely. We watched interactions and mergers reshape galaxies, ring galaxies from direct collisions, polar ring galaxies from unusual accretion events, peculiar galaxies with tidal tails and shells, jellyfish galaxies in the middle of being stripped in a cluster environment. All of these are stages in stories still unfolding. And finally, we saw galaxies classified by their activity. Starburst galaxies converting gas into stars at furious rates. Seyfert galaxies with actively feeding central black holes. Radio galaxies launching relativistic jets across enormous distances. Quasars, blazars, and radio-loud active nuclei as different faces of the same underlying phenomenon, seen at different luminosities and orientations. Through all of this, one message keeps returning. Galaxy type is not a permanent label, it is a description of what a galaxy is doing right now, given its history so far. A spiral can become a lenticular after losing its gas. A gas-rich merger could become a starburst, and then an elliptical. A quiet elliptical can wake up into an active nucleus if fresh gas reaches its center. An active galaxy can quiet down when its fuel runs out. The universe is not a static museum of 18 fixed species. It is a living, evolving population of systems, each shaped by its dark matter halo, its gas supply, its merger history, its environment, and its central black hole. Here is the causal chain that runs through all of it. Dark matter forms halos in the early universe, providing gravitational cradles. Gas falls into those halos, retains angular momentum, and cools into disks or falls chaotically into ellipsoidal shapes. Stars form. Feedback from stars, both winds and supernovae, redistributes gas and can drive it out of small galaxies entirely. Mergers and interactions reshape disks, trigger starbursts, and build ellipticals. Central black holes wake up when they are fed and go quiet when they are not, and their feedback couples to the surrounding gas in ways that can either shut down or spark new star formation. Over cosmic time, galaxies move through several of the categories we have talked about, sometimes multiple times. When you look up at the night sky, the band of the Milky Way stretching overhead is a barred spiral seen from the inside. Andromeda, if you can find it as a faint smudge in a dark sky, is another spiral, larger and hosting many more stars, currently drifting toward our galaxy on a course that will merge the two in about 4.5 billion years. The result will not be a spiral. It will be something more like a giant elliptical, built by the collision of two disks and shaped by everything we had talked about. Feedback, gas dynamics, black hole growth, merger physics. Somewhere else in the universe, right now, a dwarf spheroidal is being tidally shredded by a larger neighbor. A quiet elliptical is having a stream of fresh gas fall onto it, waking its central black hole from a long sleep. A young galaxy at the edge of the observable universe is forming stars 100 times faster than the Milky Way, blazing in the infrared behind veils of dust. A giant CD galaxy at the center of a rich cluster is silently absorbing the outer stars of yet another satellite that came too close. All of these are galaxies. All of them belong somewhere in the family portrait we have walked through tonight. And you, sitting here, are made of atoms that were forged inside stars, that were themselves born inside a galaxy that has been evolving for over 10 billion years. The iron in your blood, the oxygen you breathe, the calcium in your bones, all of it was cooked in stellar interiors, released by supernovae, and mixed through the gas of a galaxy that eventually formed our Sun and Earth. Every category we have discussed tonight is not just an astronomical curiosity. It is a piece of the story that produced you. The universe does not have one design for a galaxy. It has spirals and ellipticals, dwarfs and giants, starbursts and quiet quench systems, rings and polar rings, active nuclei blazing and dormant black holes sleeping in the dark. Each galaxy is the result of everything that has happened to it since its dark matter halo first collapsed. Each galaxy is a snapshot, and each snapshot is a chapter in an unfinished story that stretches back to the first moments of the universe and forward into a future longer than we can easily imagine. The next time you look up at the night sky, remember what you have seen tonight. That soft band of light is one of trillions of galaxies. It is a barred spiral, a starburst quiet galaxy, a home to a dormant but massive central black hole, a rotating disk carrying hundreds of billions of stars around a common center. It is your galaxy. And now, having walked through the family of every major kind of galaxy the universe knows how to make, you can look up and understand a little better what you are really seeing when you look at that light. Thank you for taking this journey. If you enjoyed it, a like or a subscribe would mean the world to me and help this channel keep making these deep explorations. And remember, the sky above you is not just a collection of stars, it is a galaxy, one shape among many, one story among trillions. Good night, and may you never look at the Milky Way the same way again.